problem. Take a look.
The sun's core is the hottest part of the sun, but our star's temperature doesn't behave as you might expect. The core is roughly 27 million degrees Fahrenheit and 10 times more dense than gold. As you move outward, the layers of the sun become cooler and less dense. Something unusual, however, occurs when you reach the outermost layer. While the surface is around 10,000 degrees Fahrenheit, the corona, the sun's outer atmosphere, is several hundred times hotter. That's the opposite of what happens with a fire. When it gets cooler, the farther away you get. Scientists call this the coronal heating problem, and evidence for this was first uncovered during an eclipse in the 1800s. The corona is usually hard to see. It's too dim to be seen next to the sun's bright body, but it can be seen with the naked eye when the moon blocks the sun during a total solar eclipse. To understand how this mystery was discovered, it helps to know how scientists started studying the chemical properties of materials on Earth. In the early 1800s, instruments named spectroscopes were invented to identify materials that emit light when heated. Light enters the spectroscope and is filtered through a tiny hole to isolate a single area. It then bounces off a special grating that disperses light into its different wavelengths. While sunlight contains every wavelength, scientists discovered that every chemical element and compound contains a unique pattern of wavelengths that allows scientists to determine the composition of light sources. It wasn't long before astronomers started extracting information from the light of distant stellar objects. In 1869, two scientists independently decided to point a spectroscope toward the corona during a total solar eclipse. As the sun's light disappeared, the pattern of wavelengths changed. They saw something they had never seen before. A bright green line that did not relate to any element found on Earth. For a short while, scientists named it coronium. It wasn't until 70 years later that a Swedish scientist discovered that these lines were the result of elements such as iron being stripped of its electrons. Every element has a specific number of electrons surrounding the nucleus. As each electron is removed, more energy is needed to remove the next one. The green line shows that iron has been stripped of 13 of its 26 electrons, indicating that the corona needed to be millions of degrees, counterintuitively far hotter than the sun's surface. Scientists have since proposed a variety of theories for what mechanisms could be adding that extra heat into the atmosphere. One theory suggests that small waves in the sun's surface pushes particles and heat into the atmosphere, a bit like how ocean waves push surfers. Another theory suggests small bomb-like explosions from the realignment of the sun's magnetic field create heat. Many scientists think it may be a mix of both. We've studied the corona from Earth during many eclipses, but to solve our star's biggest mystery, we have to make direct observations from the region itself.
We just heard great news. The signal acquisition has been confirmed. So another check on the list of things that need to go right today. And so that list is coming together very beautifully. We're going to send you now out to NASA Edge's Franklin Fitzgerald to take a look and talk to an astrophysicist, a solar astrophysicist. Franklin?
Thank you, Joshua. Yeah, I'm here with Dr. Alex Young, who is an astrophysicist from Goddard. Alex, how are you today?
I'm doing fantastic. How are you?
I'm doing pretty good. You saw the launch from Banana Creek. How was it?
It was spectacular. It was so spectacular. It's not the first launch, but it's the first time I've seen one from there, and it was amazing. And being with that crowd was amazing.
That is good to hear. Now, I know you are very interested in getting to the science of solar orbiter. Tell me about what you most are looking forward to.
Well, one of the most obvious things that comes to mind is the unique view of the poles. We have never imaged the poles of the sun. We've never gathered detailed magnetic field observations of the poles directly. And that's a really, really important thing for understanding the sun's activity cycle. And so that is really, really critical because that's what, the sun's magnetic activity drives space weather. And so this is going to be a game changer with these kind of observations from Solar Orbiter.
Now, you got a couple years until you start gathering data from Solar Orbiter, but you do have a recent solar mission where you've been receiving some data, and that's Parker Solar Probe. Can you give us a little update on that?
Yeah, so Parker Solar Probe has already been around the sun 3 times. It's going to make 24 orbits, and each one, it's every time it passes Venus, which will give it a little kick, it'll get closer and closer. But they've already brought back data. They've already brought back tons of data and have gathered amazing number of questions that they hadn't expected. They've made amazing discoveries already. They haven't even gotten to the final goal. And we have a new understanding already of the turbulence, sort of the region where the solar wind becomes turbulent, where the solar wind sort of relaxes. We found out that the magnetic fields that come away from the sun actually do these crazy 180 turns